PrivacyScope, automatic analysis of private data leakage in DEE-protected applications. Virginia Political Institute and the State University of Lecture 3. Abstract. Big data analytics is having a profound impact on many sectors of the economy by transforming raw data into actionable intelligence. However, increased use of sensitive business and private personal data with no or limited privacy safeguards has raised great concerns among individuals and the government regulators. To address the growing tensions between the need for data utility and the demand for data privacy, trusted execution environment (DEE) is being used in academic research as well as industrial application as a powerful primitive to enable confidential computation on the private data with only the result disclosed but not the original private data. While much of the current research has been focusing on protecting the DEE against attacks, slides and information leakage, the security and privacy of the application executing inside the DEE enclave has received little attention. The general attitude is that the application is running inside a trust computing-based TCP, and therefore can be trusted. This assumption may not be valid when it comes to unverified third-party applications. In this paper, we present PrivacyScope, a static code analyzer designed to detect leakage of private data by an application code running in DEE. PrivacyScope accomplishes this by analyzing the application code and identifying violations of the property called non-reversibility. We introduced non-reversibility since the classical non-interference property falls short of detecting private data leakage in certain scenarios. In machine learning program, where the program output is always related to private input data, given its strict reliance on observable state, the non-interference falls short of detecting private data leakage in these situations. By design, PrivacyScope detects both explicit and implicit information leakage. The non-reversibility property is formally defined based on the non-interference property. Additionally, we describe the algorithms for PrivacyScope as extension to the runtime semantics of a general language to evaluate the efficacy of our approach and the proof of feasibility prototype. We apply PrivacyScope to detect the data leakage in select open source ML machine learning code modules including linear progression, k-means clustering, and collaborative filtering. Also, PrivacyScope can detect intentional data leakage code injected by a programmer. We responsibly disclose all the discovered vulnerabilities leading to disclosure of private data in the open source machine learning program being analyzed. Index terms, information flow analysis, privacy, interest, EGX enclave, static analysis, symbol execution, taint analysis, formal semantics of machine learning, Internet of Things. Introduction. With more and more data being collected and analyzed, there is an increasing concern on privacy implications of the sensitivity of information of individuals. While we are enjoying such rapid advancement in the data science, many consider this a step backward on the fundamental civil right to privacy. In the effort to tackle this fundamental trade-off between data utility and data privacy, much work has been done to enable secure computation on confidential data, where only the results are revealed but not the original data. Secure computation techniques are generally divided into two categories: cryptography techniques and system mechanisms. Trusted execution environment (TE) is one of the more popular system methods designed to ensure secure computation of private data given its ability to host arbitrary computation with limited overhead. However, even though techniques leveraging TE aim at providing privacy assurance to users, the security protection of a system actually depends on both the TE and the TE-protected applications themselves. For example, while the Intel XGX architecture can guarantee the integrity and the confidentiality of execution, it does not address leakage of private data due to program code vulnerabilities or intentionally injected backdoors within SGX-protected program. The code executing in a SGX enclave can inadvertently or maliciously leak private data outside its trust boundary. Major of recent research 5 to 7 focus on addressing potential data leakage on TE, while few books focus on private data leakage by TE-protected applications themselves. Since TE-protected applications may contain malicious logic embedded by attacker or data leakage bugs brought by programmers, it is important for users of these secure applications to audit and validate them. However, ensuring trustworthiness of TE-protected application manually requires security expertise and is not scalable for a large amount of TE-protected applications. Therefore, an automatic verification tool for users to detect leakage in TE-protected application is desired. A formally specific semantics of TE-protected application and applies classical information flow analysis 9 to automatically detect leakage on it. The classical information flow analysis applies the non-interference leakage on it. The classical information flows analysis applies the non-interference property that essentially ensures no mutation of sensitive data can lead to observable changes in program state from the perspective of an outside observer. However, the non-interference property is not suitable for widely adopted machine learning algorithms in the era of IoT and cloud computing. Machine learning algorithms use private data to train models which are observable for cloud service provider. Those machine learning programs always violate classical non-interference property. Therefore, a new property is desired for defining information leakage in machine learning programs. Inspired by a non-interference property, we formally define non-reversibility property of enclave application in this paper. Violation of a non-reversibility property implies malicious actor can infer sensitive input by observing the output generated by program code running in an enclave. Thus, non-reversibility is applicable to analyzing data leakage issues in widely adopted machine learning code modules. Detecting violation of non-reversibility is challenging. There are fundamental challenges that are different from non-interference. First, it is not trivial to determine if the recovery from output to input is deterministic or not. Second, even if there is a data flow from sensitive input to output, it is not entirely clear what the exact relationship is between input and output. What is crucial in determining recoverability To tackle these challenges, we designed and developed PrivacyScope, a static code analyzer that detects violations of the non-reversibility property by enclave program code. PrivacyScope employs simple execution to track propagation of private data and record past conditions. When program branches throughout the exploration based on a simple program input. At the conclusion of program analysis, PrivacyScope generates a report detailing any leakage of private data. PrivacyScope works seamlessly with the secure development environment. As a demonstration, we extend the Intel SGX software development ecosystem with the PrivacyScope to automatically detect violation of non-reversibility property on enclave modules. The main contribution of the work are as following. We formally define non-reversibility property to characterize the notion of secret data leakage in machine learning programs. Inspired by non-interference property, non-reversibility accomplishes this by establishing a deterministic relationship between program input and output in TEE-protected application. We construct a primer language to formally describe our proposed innovative approach. PrivacyScope, which automatically detects violation of the non-reversibility property in TEE-protected application. We present a proof of feasibility implementations of PrivacyScope leveraging the Clang static analyzer and demonstrated the viability and efficacy of our approach by evaluating its performance by analyzing select machine learning applications executing in Intel SGX enclaves. Background: Intel SGX. Intel Software Card Extensions (SGX) is an extension of the Intel processor architecture designed to safeguard code and data against unauthorized modification and disclosure. The SGX guarantees the integrity and the confidentiality of user code and data by providing a processor-hardened, processor-protected, trusted execution environment called an enclave. A user application executing within an enclave is subject to heightened security measures enforced by the processor. Remote attestation, key and credential provisioning are other critical features of the Intel SGX architecture. Remote attestation allows a remote party to verify the authenticity of application code module executing inside an enclave. Despite its strengths, SGX suffers from several hardware security limitations, including SGX page fault, cache timing, address bus monitoring, and processor monitoring. Fifth, there has been research working on addressing these limitations, like defending against the cache timing attacks in TANs. We consider these security limitations orthogonal to our intent of this paper and believe these limitations must be addressed independently from PrivacyScope. B. Symbol execution. Symbol execution is a popular program analysis technique that dates back to the 1970s to test whether certain properties can be violated by a piece of the software. 11 and 12. The key idea is allow program to take on symbol inputs. Then the program is abstractly interpreted by a symbol execution engine. During interpretation, best condition and symbol memory stored are recorded for each explored control flow path. By symbolically interpreting TE-protected applications, PrivacyScope logs symbol expressions of targeted input argument and use logs information to track any explicit leakages. Additionally, by tracking target input argument in path conditions and by combining the information with the result from the application, PrivacyScope can detect any implicit leakages. An alternative way to find explicit leakage is to use data flow analysis (DFA) frameworks 13 and 14. Symbolic execution is order more complex in terms of complexity comparing to DFA. However, most data flow frameworks are passive incentives and are hard to be used for finding implicit leakages. Current State Analyzer. The Current State Analyzer is an open source analysis tool for finding bugs in C++, C++, and Objective-C programming during complication phase. The analyzer is a symbolic execution engine that abstractly interprets program codes and traces out possible execution paths. After generating the possible execution paths, the analyzer performs conceptually a reachability analysis. During the analysis, the analyzer enters predefined bug checkers. A bug is found by hitting a state where some violation of checking invariant are satisfied. PrivacyScope is a special checker we created which implemented on top of Current State Analyzer for identifying explicit and implicit leakage of enclave program. Current State Analyzer leverages a region-based memory model to perform path-sensitive symbolic program analysis. The analyzer can process most forms of C expressions containing arbitrary levels of pointer dereferencing, pointer arithmetics, composite arrays, and structured data types, arbitrary typecast, dynamic memory allocations, etc. These features are critical to PrivacyScope. Even the pointer operation is commonplace in C++ code, and composite structure are widely used in our C++ software, including data analytics modules. Strict model and assumptions. The goal of PrivacyScope is to discover deterministic leakage of user private data of an machine learning application. The strict model follows that of TEE-based secure computation. User private data are encrypted for storage outside the environment, and when they used for training the model, the data is decrypted only side in the container for consumption. With the recent advances in machine learning along the leakage with the packaging, it is becoming increasingly accessible to the general public, even to those without machine learning background. As privacy concerns continue to grow, it is likely that majority of the computation on user data will be conducted in a privacy-preserving manner, and the security of the applications running in the container, which are granted unlimited access to user private data, will be crucial in user privacy protection. However, with new customizations of individual training methods for various application domains, it can be very challenging for individual user of machine learning system. Potentially without an expertise on programming language, information flow, and machine learning to recognize subtle ways the machine learning applications can deterministically leak user data. As a result, we assume that there can be unintentional or intentional logic in the TE protected application that will leak contained deterministically. PrivacyScope is a detection framework that can take under defined privacy leakage rules written as pre-machine learning language extension details section VA and automatically analyze TEE protected program to see if there is any deterministic information flowing from the input, such as private data, to the output, such as machine learning models. Although PrivacyScope aims at preventing the DE-protected application from leaking users' private data in a deterministic manner. It is not designed to detect potential information leakage due to various side channels or convert channels. We provide a brief discussion in section 8A on potential extension to protect against the side convert channel information leakage. Non-reversibility property. In traditional definition of secret leakage for user keep her data confidential, she would define a policy stating that change of her confidential data cannot affect any publicly observable data. This policy allows programs to perform manipulation and modification on secret data, as long as any observable outputs of these programs do not reveal information about the secret data. Since this policy states that no visible public data is interfered with confidential data, this sort of policy is called non-interference policy. 16. Intuitively, non-interference for program guarantees that a variation of confidential high inputs does not cause variation of public low inputs. 17. However, non-interference policy is not suitable for our scenarios. In our scenario, machine learning algorithm sits in enclave. We view secret inputs received by enclave as high and the training output to the cloud server as low. In traditional definition, any change of high data would not interfere with the raw data, but our output trained model changes according to receive input secret data. In case non-interference policy is always violated in machine learning algorithms, thus we need a final grade policy. In contrast to non-interference, we define non-reversibility to guarantee that a variation of a single confidential high input could cause a variation of public low outputs. But keeping this single confidential high input and low inputs on changes will not always lead to the same public low outputs. We provide the formalization of non-reversibility in the following. We extend the notation from 17 and rigorously formalize non-interference and non-reversibility using the machinery of programming language semantics. We assume that computation starts in the input stage SH, SL, .sh, and SL contains the initial values of variables high and low respectively. SH represents any single variables inside SH, and SL represents any single variables inside SL. The program either terminates in an output stage S prime, SH prime, S prime N, with output values for the high and low variables, or diverges. Thus the semantics P of the program P is a function of P synchron S, where say S scope, which maps an input state S. Phase terminator. We define the equivalence relations L and H means two states are the same if they are equal on all the low variables if and only operand means there exist on variables inside the high variables are the same two statements. SH S prime if and only if SH equal SH prime. We characterize the observation power of the attacker by the relation on behaviors such that two behaviors are related by SL. If and only if they are distinguishable to the attacker. Relation implies that the attacker can observe the raw variables. For given semantic models, no interference is formalized as follows. P is secure if and only if offer S1, S2, S1 equal L, S2 equal P. This is if two input states are share the same raw values, then the behavior of program executed on these states are indistinguishable by the attacker. Whereas non-reversibility is formalized as below. P is secure if and only if. Which reads if two states are the same values, if two input states share the same raw values and the same values of one single high variable, then there exists one other high variable that when it is different for the two input states, attacker will observe the different behaviors of the program executed on these states. If this other high variable does not exist, then one single high variable will be leaked and the P will not be secure, because the attacker would be able to look at P and reverse the relative computation of the single high variables. According to the former definition of non-reversibility, the program L H1 plus 4 is insecure and the value of H1 can be inferred by attacker by observing L. However, the program L equal H1 plus 4 plus H2 is secure if H2 is changed. L observed by attacker will also be changed and attacker cannot infer value of H1 without knowledge of H2. Note that the probability distribution of inferring H1 from L will thus be determined by H2 in this case. PrivacyScope, a general language primer. For precise declaration of how PrivacyScope works under the hood, we extension notation in 18 and introduced a language called primer. PrivacyScope intermediate range. PrivacyScope intermediate range. PrivacyScope intermediate range is used for precise declaration purpose, while no compiler or symbol execution engine is implemented for PrivacyScope intermediate range. We created PrivacyScope intermediate range because of the complex semantic model of C++ language. PrivacyScope intermediate range captures the primer semantic model of C++. We describe how PrivacyScope analyze programs written in PrivacyScope intermediate range to reveal the core ideas. In addition to the PrivacyScope intermediate range examples in the sections, we also show how PrivacyScope is implemented on the top Clang static analyzer and is applied to C++ enclave modules in section 3. Section 6. The backwards normal form grammar for PrivacyScope intermediate range presented below. PrivacyScope intermediate range program is composed of the sequence of statements. The statement consists of assignment and conditional branches. By design of PrivacyScope intermediate range expressions are free from any side effects. They do not change the program state. We use the and B and U to present binary additions, subtraction, etc., and unary operations, logical negations, exclusive OR, and etc., respectively. The statement gets secret retrieves high variable from secret while the statement declassifies uncovers a value to the outside world. This is potentially observed for the malicious actor. For simplicity, we only consider expressions, constant, variables, etc., which evaluate to 32-bit integer values. We also omit the type checking semantics of Premier and PrivacyScope intermediate ranges and assume all programs under evaluation are well typed. For example, binary operand are integers of variables. The operation semantics The operation semantics of the language specify unambiguously how the program should be interpreted in the language. We first define the base operation semantics before we specify program analysis. Each statement rule is of the form. Computation, current state, statement, end state, statement per computation. Rules are read from the bottom up and the left to right. Given a statement, the PrivacyScope intermediate range interpret pattern matches at the statement to find the applicable rule. For instance, the statement XE is interpreted according to assigned rules. Then the interpreter evaluates the computation given on the top of the rule, and if successful, transition to the end state. If no rule matches, then the machine heart abnormally maps a variable to each value for given execution context. For example, denote the current value of variables. We denote updating a context variable x with value v as xv. Thus, updating the value of the variable x to the value 10 in context delta is denoted as delta x 10. We denoted evaluation of the expression e to a value v in the context of the delta by delta e v PrivacyScope intermediate range interpreter evaluate the expression e by matching e an expression evaluation rules and performing the corresponding computation. The complete operation semantics for PrivacyScope intermediate ranges are shown below. In addition, the context and the statement skip indicate a termination. Private program analysis. In the section, we described how to PrivacyScope analyze program written in PrivacyScope intermediate range. We present how PrivacyScope works. PrivacyScope intermediate range to see the right upon how PrivacyScope works for C++. The objective of the analysis is to detect any violation of non-reversibility property in PrivacyScope intermediate range programs. PrivacyScope achieves this by combining taint tracking and forwarding symbolic executions. Taint tracking is used to track the flow of high information from each sources to each sink. Forward symbolic execution is used to reason about the behavior of the program under the analysis given initial inputs. PrivacyScope represents the past condition of program execution as a logical formula, thus reducing the reasoning of program behavior to domain of logic. PrivacyScope represents variables symbolically, thus can examine program execution spanning multiple input space of the program at one time. Table 1. PrivacyScope policy of non-reversibility violation. We express PrivacyScope in terms of the operation semantical PrivacyScope intermediate language to keep track of the taint status for each program value. We reduce various PrivacyScope intermediate language to be tuple of the form VT, where V is the value in the initial range. RT is the taint status of VR is modeled by security semi-lattice with join operation only shown in figure 1. In this semi-lattice, sensitive data is labeled by T1, T2, and more. If a variable is labeled by, it means it is not sensitive, while if a variable is labeled by it means it is tainted by two or more tainted sources. So revealing it would not break non-reversibility. We also introduce a new mapping which maps variables to taint status. Security semi-lattice for taint status. To enable forward symbolic execution in Premiere, we introduce the following changes to Premiere. PrivacyScope intermediate range. Value 32-bit integer execute. Pi contains current constraint on the symbolic variables due to past branches. These changes make partially evaluated symbolic expressions valid for the value in PrivacyScope intermediate range. Thus, when getSecret is evaluated symbolically, it can return a symbol instead of a concrete value. Trust table of P binomial T1, T2, and B constraint T1, T2. After introducing the aforementioned changes, Table 1 presents a PrivacyScope policy for detecting a non-reversibility violation. It introduced taint status into the system by marking up or values returned by getSecret with a different taint status. Taint is propagated through the program according to propagation rules. For constraint, they are labeled as insensitive. For assignment and unary operations on a variable, they keep same taint label for the variable. Figure 2 shows taint label propagation rules for binary operation and conditional branches. The policy checks declassify leaks secret whenever a value is revealed. Algorithm 1 declassify process. It first checks if the variable is labeled as sensitive. If yes, it reports an explicit leakage. If no, it then checks if the path constraint is sensitive. It uses a hash map to assist with checking whether the revealed variable differs in distinct branches. Finally, at the end of the last path interpretation, declassify checks if there is any item in hashmap HM. If so, concludes that there is an implicit violation of non-reversibility. Note that this last step is omitted by algorithm 1. To simplify the explanation, we summarize the private scope operation semantics as follows. PSD class. Next, we present a simplified code segment written in PrivacyScope intermediate language to further explain the program analysis function of PrivacyScope. Consider the following program: H1 2 gets crate, H2 3 gets crate, X. We can easily see that declassifying X does not violate the non-reversibility property. Knowledge of the value of the X does not immediately reveal the value of the first secret. However, declassifying H1 allows attacker to infer the value of the first secret by dividing the observed value with 2. Table 2 represents a simulation of how PrivacyScope detects a leakage. Row 5 are leakage since the taint status H1 is T1, while row 4 does not because the taint status of X is T. Consider the following code snippet. By observing the declassified output, an attacker can easily infer H is equal to 19 or not, and ultimately recover that the secret. Table 3 illustrates how PrivacyScope detects implicit leakage. Row 3, for instance, reports a leakage since the taint status for pi is T1, and the values retrieved from the hashmap HM is 0, which is different from the declassified outputting 1. Row 2 of the table 3, on the other hand, doesn't report a leakage even though the taint status for pi is T1, because nothing is stored in the hashmap HM before the interpretation. Incorporating PrivacyScope is an Intel-SGX enclave. Intel-SGX enclave modules are typically written in C++. Therefore, the following the part of incorporation of formation's core ideas written in PrivacyScope intermediate language and present how PrivacyScope is integrated into Intel SGX ecosystem. Each Intel SGX enclave declares one or more entry points into the enclave. Referred to encores by the Intel SGX SDK, these interface allow untrusted outside applications to access trusted code running inside the enclave. An enclave may also have OCurs, which allows trusted enclave code to call out to the untrusted application. To configure an application to run an Intel SGX enclave, an enclave interface definition file is created. An EDL file resembles a traditional C header file and contains prototype declarations for all equals and OCurs interface. The enclave EDL file defines how data is marshaled between enclave trusted code and outside untrusted applications. To pass secret data enclave code for further processing, enclave use equals type interface. Similar to C function prototypes, the equals interface parameters are annotated with the attribute like in and or out. A parameter with in attribute is used to marshal data from outside untrusted application into the enclave. So in our example, script data is passed into enclave via in parameters. Interface parameters without attribute are used to marshal data from inside the enclave to the outside untrusted application. The Intel SGX abstract out the details of the data marshalling by generating the necessary proxy code. In short, in parameters correspond to the get secret in the previous section. Prior to performing code analysis, PrivacyScope processes an XML configuration file provided by user containing function names that the user is interested in evaluating. PrivacyScope also extracts information included in the SGX EDR configuration file. Following a quick initialization step, PrivacyScope analyzes program code using the approach outlined in the previous section and generates a report summarizing the outcome of the code analysis, including any violations of non-reversibility property. For explicit information leakage cases, the report describes how program output can be used to infer each secret input, thus assisting developers in securing their code. For implicit information leakage in the report provides past conditions and the return results which can result in leakage of secret data. Evaluations implementation. For our proof of concept prototype, we use the Intel SGX SDK version 2.0 construct the trust application running in SGX enclave powered by an Intel NUC running under the Ubuntu 14.04 TLS, built on the top of Clang version 7.00. We built a prototype of PrivacyScope of adding over one cloud. We have evaluated the prototype of PrivacyScope by porting open source machine learning programs written in C++ Intel SGX enclaves and analyzing the enclaves modules for data leakage. Illustration. A leakage example in C. To illustrate the PrivacyScope operation on real Intel SGX enclaves modules written in C, we provide an illustrating example. For simplicity, our example neglects description of secret data. However, PrivacyScope does not consider the description of the encrypted secret data. It records the description function names from the Intel SGX IPP library in the predefined list. And when PrivacyScope meets predefined description functions, it assigns the symbol value of secret data to descripted secret data. For illustration, we defined equals function in EDR file for processing secret data as int enclave process secret in secret outputs. Source code of enclave process secret function is shown in list 1. In the simplified example, we can easily see that the secret 0 is explicitly leaked and secret is implicitly leaked. Code snippet of illustrative example in C. Next, we showed how PrivacyScope explores the illustrative example and identifies explicit and implicit privacy leakage using symbolic execution engine of Clang static analyzer. First, we need to define the state that the symbolic execution engine must maintain. We define the state as a full-tuple STMP environment similar to Fives, where STMP represents the next statement in the source code to be evaluated. In our illustrative example, the STMP can be an assignment, a conditional branch, or return statement. env is an environment which maps from L value. L value is an expression with an object type according to C standard expressions to memory regions. Abstract representation of the memory object, register I. A memory region can be sub-region of another region, and when a variable of array type is defined, it has sub-objects called elements. For array elements, we have an element region like register I with its super region register I to represent the array region. As for when a pointer pointing to some unknown memory block, we have a sim region sim region for representing the memory block pointed to by the symbolic pointer. Sim region represent a region that serves as an alias for either a real region, a null pointer, etc. It essentially is used to map the concept of symbolic values into the domain regions. Is a store which maps from the memory region's concrete values, symbolic values, alpha, I, or memory region's register I. Pi denotes path constraints on the symbolic values. At the beginning of the symbolic execution, pi is set to true. As the symbolic execution engine explores the program statement, pi grows when branches are met and assumptions. When taking any branches are recorded at pi formula. This formula indicates how execution can reach any statement in the program code under the analysis. Depends on the statement, the symbolic engine of current statement analyzer changes state as follows. The evaluation of the assignment x equal e updates the environment and the store theta. E can be legal expression involving unary and binary operations over symbolic or concrete values. If E contains unknown L-value expressions in the context of a current execution state, new registration initializer for the unknown expressions is updated environment, and the mapping between newly initialized register I and context of current execution state is created in updated theta, assuming ES is the symbolic expression of the evaluating E. ES is associated with X is updated environment. The evaluation of the conditional branch if E then statement S true is statement S first affect the path constraint pi. When conditional branch is met, the symbolic engine will fork and create two execution states, one with path condition pi true, pi per E, and the other pi false, pi where yes. Symbolic expression by evaluating E. Symbolic engine will follow the two newly created execution states by one. Tables represent the symbolic exploration of the illustrative example. Initially, execution state A. The path condition is set to true, and environment and the theta are null. During the evaluation of the right to right-hand side RHS, the first evaluated expression is secret. So new region register 0 is generated and associated with the secret environment, and region 0 is mapped as sim region in theta. Then it follows the evaluation of secret 0, which leads to a new expression region map of secret 0 to registry 1 in environment. It is also updated with a new map of the registry 1 to register 0. After the evaluation RHS, the result register 1 plus 100 is associated with the temporary. Next, execution state B, evaluation of the RHS of the line 3 returns register 1 plus 101 within the execution context, and the result is associated with the evaluation of the line 3 left-hand side RHS. The evaluation of the line 3 LHS brings a new region registry 2, and it is associated with the output environment. Meanwhile, registry 2 is mapped to sim region in theta. Besides the result of the line 3 RHS, registry 1 101 is associated with output 0 in environment. When conditional branch is met, execution state C, the engine will fork into two execution statements D and E with opposite path constraint on the comparison statement. During the execution of the state C, a new region register 3 is assigned to secret 1 in environment, and register 3 is an element region of the register 0. By evaluating the comparison statement, the two opposite path conditions, register 0, 1 equal 0 and register 0, 1 equal 0 are added to the pie of execution statements D and E. The evaluation of the return statement called the procedure of policy checker, similar to previous P declassify check. When PrivacyScope starts exploring the target function enclave processing data, it first goes into EDL files and fetches parameters as specified by user's predefined rules. If no rules are predefined, the default action is marked out attribute parameters as potential leaking point, and inattribute parameters are as secret. The PrivacyScope will start exploration of source code described in previous paragraph. During the exploration, PrivacyScope introduces taint status to secret variables and propagate the training as mentioned in program analysis for pre-machine learning when enclave process data function return or ends. PrivacyScope performs a policy check simply similar to P declassify check for explicit privacy leakage check. PrivacyScope checks our parameters to see their taint status. In the illustrative example case, output 0 is tainted by T1, so output 0 explicitly leaks the private value of secret 0. For implicit privacy leakage check, PrivacyScope utilizes hashmap HM and find that the return values are different for different pi, which branches on sub-object of secret. The warning report generated for the illustrative example is shown in box 1. Performance evaluation. Our primary object is to detect any violation of non-reversibility property in the truth code executing inside the SDX enclave. However, current version of SGX SDX does not support easy migration of legacy application. Even if it is written in C++, there is no existing open source implementation of machine learning algorithms implemented inside the enclave using the Intel SGX SDX. Thus, we had to port open source machine learning algorithms so that they can execute it inside the SGX enclave. We selected 3 popular open source machine learning projects from the public GitHub repository and ported them using the Intel SGX SDX. They included the linear regressions. K-means and recommender 27 to 29. To evaluate the efficacy of the PrivacyScope, we inserted molecules code inside the ported machine learning code. The results are examined by the authors, and the efficacy of PrivacyScope solution was verified by the authors manually. During this process, we also detected multiple pre-existing secret leakage in the open source recommender implementation. We provide a detailed explanation of these findings in the next section. Table 5 summarizes the performance data, including the PrivacyScope code analysis time for each of the 3 open source machine learning projects. The analysis time was measured using a Linux OS operating system built-in time utility. The total execution time was computed by summing up the user and system times. Case studies. The goal of PrivacyScope is to assist user and developers in identifying potential information leakage vulnerabilities in program code intended to run in the TEE-protected environment. PrivacyScope accomplishes this objective by identifying any violations of the non-reversibility property In this section, we present two case studies to demonstrate PrivacyScope's capabilities by analyzing the behavior of two open-source machine learning programs. These two examples by no means cover all the possible scenarios. In the first case, PrivacyScope uncovers implementation defects caused by inadvertent coding errors during software development. In the second case, we illustrate how PrivacyScope can detect malicious code inserted into the codebase by malicious actor, finding information leakage in Recommender. Our first case study is analysis of the C library for product recommendations suggestions using the collaborative filtering CF727. Recommend analysis and runs from the collective feedback of a large number of users. It then uses user preference to predict and recommend the most appropriate product for a particular user. We found 6 violations of the non-reversibility property in the open source machine learning project. We detailed this process in Appendix 13, verifying effectiveness of PrivacyScope in Cambridge. Our second case study, mimicking a miraculous enclave writer and embedding sensitive data leakage logic inside the enclave programs. We add explicit and implicit leakage logic to open source machine learning program Cambridge 29th. We show the details of how we inserted miraculous logics in Appendix 13. Information flows related to information flows analysis method. Use of the information flow analysis to detect information leakage within programs has been the subject of much research in the past decade. Language-specific methods typically augment type systems so that they can statically check the flow of the private data within programs that manipulate the data. 9. For example, integrate information flow analysis into the Java language type system. While 9, 25, 26 propose innovative analysis methods for imperative and concurrent language. 21 detects security vulnerabilities in hardware design written in HDL. In these solutions, they focus on addressing the non-interference property in programs. In addition to the aforementioned information flow analysis, the plethora of methods have focused on detecting, measuring, and understanding the nature of privacy leakage on different platforms. Static and dynamic tainting analysis are two major categories of methods for detecting privacy leakage. Dynamic method typically monitors the system at runtime and examining the system as it executed the code. Static methods, on the other hand, use compile time analysis to predict the impact of the code execution on private data. Static methods can have a higher false positive rate as compared to the dynamic method. 2320 leverages dynamic tainting to detect intentional leakage of private data in the Android operating system environment, while 22 examines system-wide information flow for malware detection in the Windows platform. Finally, ACE uses model checking to verify the information flow properties of code running in the trusted enclaves. Table 3 summarizes key recent research work in the area information analysis method, highlighting the target environment for each approaches. B. Secure systems on trusted hardware. There have been many recent advances in the area of trusted hardware platforms, including the development of commercial off-the-shelf secure processors. Armstrong 31 offers a processor capable of executing in the secure world as well as normal world with isolated address spaces. TPM TXT32 provide attestation on the execution state of the platform, but all privileged software must execute in the trusted computing base. SGX3336, an extension to the Intel architecture, offers confidentiality and integrity guarantees via trusted processor without without requiring any trusted on the part of the infrastructure software. Multiple secure systems have been recently built on top of these trusted hardware platforms. 224, 37, 38, VC3, 2 and OpenCode offers SGX protected data processing platform, assuming that the code execution inside each enclaves is trusted. Thus, their confidentiality guarantee is based on the assumption that enclaves code does not leak secret. In these cases, PrivacyScope can be used to confirm these assumptions. Luan and Chiron utilize sandboxing to prevent untrusted enclave module from leaking secret data from side channels. To be adopted, these methods require a certain level of trust to be established between users, service providers, and their solution. PrivacyScope can strengthen users' trust in these scenarios. All of these methods require a modicum of the trust between the user and the trusted computing platform. PrivacyScope is designed to address this concern in the Intel SGX architecture. Privacy leakage in the machine learning. Using machine learning training models on the big data poses many privacy challenges. Machine learning models can uncover and expose surprising and unexpected personally identifiable information such as relationship and associations violating privacy. 39 to 41. Take a first step to conceptualize privacy in the new era and enforce data use rules through designing new policy specification languages and corresponding enforcing systems. 14 creates a language for specification of origin-based privacy rules and implementation of prototype of a type system to enforce such policies. In 41, the author presented Leakage, a language of specified privacy specification and restricted how private data must be handled. 39. Presented tools which provide data use policy enforcement through a kernel-level compliance layer. PrivacyScope can integrate such policies and enforce more rules other than non-reversibility in the future. Discussion and future convert and side channels. In this section, we briefly highlighted potential convert channels that can be exploited to elect private data in the Intel SGX computing environment. Each converted channel compromises PrivacyScope security goals. We will address mitigation techniques to safeguard against these attacks in the future works. Timing channels. Malicious actor can infer security through recording the time spent for program executions. PrivacyScope can be extended to simulate the execution time for program paths and detect if execution time depends on secret in the future. Probabilistically channel. Malicious actor can infer secret through observing probability distribution of declassified data. Power channel. Malicious actor can measure the power consumption cost for program executions and infer secret. PrivacyScope does not address side channels brought by the hardware limitations on the Intel SGX processor itself. We consider these limitations also to PrivacyScope and we list them as following. SGX page fault. Privileged software easy. OS or hypervisor can maliciously control pages tables of an enclave to observe a memory access pattern of enclave program execution. Cache time. Side channel exists for the two processes running on the same core. These two processors can use caching time to infer knowledge of the other. Address bus monitoring. While all processes data is encrypted prior to existing the SGX processor package, a malicious user using sniffers or a modified RAM chip can monitor the address bus and achieve a memory access pattern side channels. Prior knowledge on user data. When the adversary has prior knowledge of user private data for example, knows the distribution of variable values. PrivacyScope requires that the knowledge to be incorporated in the model specification to ensure the soundness of the privacy leakage analysis. For instance, given the function f(a), b, a plus b, where a is privacy-sensitive scalar variables and b has value of 99% of the time, and 1 otherwise, then the attacker can conclude with a high degree of confidence, for example, 99%, that the output value is the same as the value of the privacy-sensitive input variables. To mitigate this problem, the users of PrivacyScope are required to incorporate the knowledge by extending PrivacyScope intermediate range and analysis engine so that it can handle with the new semantics limitation and future work. PrivacyScope is built on top of symbolic execution engine, and the symbolic execution is known to have a limitation on scalability. Although encrypted code does not have large size, they will become larger in the future. Also, our design needs encryption writer and the cloud service provider to send the user the source code encrypted for the validation. This may hurt the intellectual property of the cloud service provider in the future. We plan to analyze the binary encrypted code directly instead of CH++ code source code. This would protect the intellectual property of a cloud service provider. Conclusions. In this work, we formally defined the non-reversible property on top of the classical non-interference property, which is more suitable for machine learning problems. So using our new proposed language, PrivacyScope machine intermediate language, we describe our innovative problem analysis approach using formal semantics. PrivacyScope intermediate language formal semantics can be extended by users who wish to introduce their own specialized notion of the non-reversibility. We designed and implemented PrivacyScope, a prototype static analysis tool that implements the rules as defined in PrivacyScope intermediate language to protect the non-reversibility violation in program executed inside the Intel SGX enclave. We show the efficacy of the prototype by applying PrivacyScope to find the sensitive data leakage and miraculously embed the scope in the open source machine learning programs. Acknowledgement. This work was supported in the part of the Office of the Naval Research under the grant, U.S. National Science Foundation under Virginia Commonwealth Cyber Initiatives.